So we have already introduced before the different types of heat transfer, including conduction, convection, and radiation. In the first three chapters, we focused on conduction, plus, of course, the possibility of having energy balance where at a certain interface where conduction can be divided into convection plus radiation flux. Now uh, we'll go deeper into the convection process because before I just gave you the convective coefficient H. I didn't ask you to calculate it. Now we'll learn in these coming chapters how to calculate, how to find H, okay? And if you remember, the convective coefficient H is really complex because it's affected by a lot of parameters, like, for example, the type of surface, the geometry of the surface, its roughness, the type of fluid, if it's air or water, for example, the velocity of the fluid. So it's really a complex parameter. That's why we determine it empirically. What do we mean by this? We do experiments and we come up with expressions, formulas that can be used depending on the case that we have. For example, if it's flow over a sphere, we have formulas. Plus, we divide into laminar, turbulent, etc. So we will learn all of these in this chapter. Okay. So to start with, we in this chapter will go over the difference between forced convection and natural convection. So as the name indicates, when we say forced, this means that we are forcing air to go over our surface. So for example, here you have a fan that is blowing air over your egg. So this will lead to higher heat transfer by convection from the hot egg to air. So this is the case of forced convection. While if we keep the hot egg to cool alone under the effect, if you want, of natural air, what will happen is that we will have convection, but that is much slower than the case of forced convection. So in case of forced convection, you will have H much larger and you will be able to cool in a faster way. While in natural case, you will rely on what? What is the process of natural convection? How you will have motion of air, you remember? We call it buoyancy effects, okay, because of temperature difference. So what will happen is that air at the vicinity of the egg will be heated. And you know that as the temperature increases, the density will decrease. So you will have motion of air upward. And this upward motion will create like a current of air near the egg, which will transport heat by convection. But the convective coefficient H will be much smaller than the case with the fan because the velocity of air and close to the hot egg will be relatively small, and then this will induce smaller values of heat transfer. Okay, so we say that here convection is driven by forced motion of the fluid, while here convection is driven by buoyancy effects because due to due to difference in temperature and density difference, this will create motion of the fluid. So free convection currents refer to fluid motion induced by buoyancy forces. Buoyancy forces may arise in a fluid for which there are density gradients. So, and here why we have density gradients? Because of temperature difference. So temperature is related to density. Larger temperature will lead to lower density, and this will lead to motion of the fluid. From you know that you have, when you have the density that is lower, the particles will be lighter. They tend to move up. Okay, while particles with heavier weight, which is called air up, will move down. And this will create circulation of air around the object. Now, in heat transfer, density gradients are due to temperature gradients, as we have seen together, and the body force is the weight. So we can conclude that the definition of a buoyancy force, we have first the upward force exerted by a fluid on a body, completely or partially immersed in its gravitational field, and the magnitude of the buoyancy force will be equal to the weight of the fluid displaced by the body. This is a general definition of a buoyancy force. In fluids, you will take, for example, buoyancy force, let's say, that will lift the object up. In this course of heat transfer, the buoyancy is due to density gradients created by temperature gradients. To understand better what we mean by this, let us consider the following example. If you want to heat water, actually, this process can rely on free convection, because what will happen is the following. At the bottom level, you have a hot surface. The hot surface will lead to warmer temperatures of water at low level. So water at low level will have high temperature and relatively lower density. Because of this, small density particles will tend to move up, okay, while colder water particles will tend to move down. And this will create circulation of water currents within your water, and this will help into heating your water, okay? So this is an example of free convection that will rely just on temperature difference and density difference to create circulation of water within your system. And this will improve, if you want, the heating process. And of course, if you put a mixer here that will help, if you mix water, this is forced convection. So when you mix it, you induce higher value of H, and this will enhance the heating process. Another example of free convection, if you consider, for example, the following home, okay, and you have fire. So what will happen, how you can, if you want create circulation of air in your system, you have air close to your furnace will be heated, and hot air will be characterized by a lower density. So lighter molecules will tend to move up and will be replaced by cold air molecules that will move down. And then once these cold molecules will move down, they will be heated again, and this process will be repeated. So you will create like a circulation of air within your room, and you will help with heating your whole room. Okay. So from here, we can talk about stable and unstable temperature gradients. What do we mean by this? Uh, not, it's not sufficient to have temperature difference to create natural convection. What do we mean by this? And for example, okay, if I take the following case, if you have a room and you put the hot source from the lower side, if your hot source is from your lower side, okay, then molecules or atoms of air at low level will be heated. So they tend to move up and will be replaced by cold molecules, and this will create circulation, okay? But what if you do the opposite? And if you put the hot temperature from the upper side, if you put the hot temperature from the upper side, nothing will take place, because already from the upper side you have light molecules because air is heated, and from the lower side you have heavy molecules because air is cool, so you will not create circulation. This is why we say that to ensure if you want air motion by buoyancy effect, okay, we have a condition. Okay, we should have not only temperature difference, the temperature difference should be opposing, if you want, the gravitational field. And here gravity is downward. Okay, so you in natural cases you have light molecules up and heavier molecules down. You need to create a temperature difference in a way to oppose this gravitational field in order to create circulation. Okay, so the presence of a fluid density gradient with a body force does not ensure the existence of free convection currents. We have another condition. Okay, as we said, the condition is that if we have, for example, T2 larger than T1, while rho 2 is smaller than rho 1, then this will create circulation of our system. In the opposite case, if I put a larger temperature from the upper side, I will not induce any circulation. Okay, so this is case A. T lower plate is larger than T upper plate, and then the density decreases in the direction of the body force. So we should have, to ensure circulation of the flow, this is the condition. You should have that the density decrease should be in the direction of the body force. If you have the opposite case, you will not have motion. So if the temperature difference exceeds a critical value, conditions are unstable, and buoyancy force will be able to overcome the retarding influence of viscous forces. In this case, the body force of the denser fluid in the upper layer will exceed that acting on the lighter fluid in the lower layer, and this will lead to circulation of the airflow. The heavier fluid will go down, being warmed in the process, while the lighter fluid will rise, cooling as it moves. So this is the condition to create the circulation, okay? While if I do the opposite, so if I take the condition for which T lower plate is smaller than T upper plate, then the density no longer decreases in the direction of the body force. So we have stability in this case. You will not have any fluid motion. Why? Because already the gravity force tends to have light molecules at the upper level, okay, and a dense molecule at the lower level. So nothing will change in this case, because this is the normal scenario. While if you oppose the temperature difference, and if you put the hot temperature from the lower side, then you will create, if you have delta T high enough, you will create a buoyancy force to oppose the gravitational force. So therefore, in case A, heat transfer will take place from bottom to top, while for case B, you don't have convection, you only have heat transfer by conduction. Any question on this?
No.
Okay. Now, whenever we talk about free convection, okay, we can introduce what we call free boundary flows. Free boundary flows occur in an extensive, in principle, an infinite medium that is a quiescent fluid, motionless at location far from the source of buoyancy. Example, okay, if you have an air, if you have, let's say, a jet, okay, characterized by so if you consider a wire that is very hot, so what will happen? Close to the hot wire, air will be heated, and then density at this level will be smaller. This will induce entrainment of air from the outer environment and motion of air in the upward direction. Okay? Uh, this is the case, this is what we call a plume. Okay, so you can see this whenever you have a hot object, you can observe the formation of a plume above it, leading to upward motion of air. Now if we consider a buoyant jet, okay, so similarly you can consider whenever you have, let's say, you impose a certain for example, a jet of fluid, okay, characterized by a temperature that is larger than the outer temperature. This will also entrain air. If we take the example of air, it will entrain air from the outer side and will lead to air motion, creating a buoyancy jet. Now, in our course, we'll focus on boundary layers. What do we mean by boundary layers? So whenever you have a surface, okay, that is at a temperatures different from air, this will lead to temperature gradient, and temperature gradient will induce a fluid motion. Okay, for example, if we consider the case of free convection that is bounded by a surface. For example, if I have a vertical surface, okay, that is at high temperature, so we heat the surface. T surface is larger than T infinity. So what will happen in this case if the temperature of the surface is larger than T infinity? Air at contact with this surface will be heated. And as air is heated, okay, this will lead to upward motion of air, creating a certain, what do we mean by boundary layer? Yani, look, close to the surface, this is a fixed surface, the velocity is zero. And because you induce air motion, so you have a region where the velocity will increase, and you are entraining air from the outside environment. From the outside environment, you have quiescent fluid. So the velocity here is zero, okay? So between these 2 points, so here you have non-slip condition, zero velocity, and here also you have zero velocity. So in between, because you have air motion, this will lead to increase in velocity, then decrease in velocity. And air will move within a small region called boundary layer, okay, due to buoyancy effects. Now, we can talk about boundary layer for velocity because we have variation of velocity within the boundary. And we can talk also about temperature variation, okay? Of course, what will happen as the fluid is moving over the surface, okay, it will cool it. It will take heat from the surface. That's why you have the highest temperature of air is at the vicinity of the surface, and this temperature then will be reduced until reaching the outer temperature, the quiescent fluid temperature, T infinity. Okay? So for free convection flow could be bounded by a surface. For example, a heated vertical plate that is immersed in an extensive quiescent fluid with Ts larger than T infinity. The fluid close to the heated plate is less dense than that away from the plate, and therefore free convection flow occurs in the upward direction. The velocity profile in the boundary layer is different than that of forced convection. You know why? In forced convection, what will happen if I want to compare? If you have a surface, okay, and you blow air over the surface like this, and you have high velocity outside in the outer environment. Let's say U infinity, okay? If I want to draw here the boundary layer, it will be different. Why? Because close to the surface, the velocity is zero because of the non-slip condition. And very far from the surface, you have high velocity. So if I want to show the variation of velocity in my boundary layer, I will start here by zero, and my velocity will increase until reaching U infinity. Okay, while in natural convection, you have in the outer side also velocity of zero because it's a quiescent fluid and you have only motion of air inside your boundary layer. While in forced convection, the highest velocity will be outside the boundary layer. Okay? Question on this? Okay. So for example, a heated vertical plate that is immersed in an extensive quiescent fluid with Ts larger than T infinity, the fluid that is close to the heated plate is less dense than away from the plate, and therefore free convection flow will occur. While if we consider forced convection, at y, when y tends to infinity, the velocity is large. While here, when y tends to infinity, the velocity is zero in case of natural convection. Okay, now we introduced the idea of a free convection, but what about formulas? What about equations So we'll understand now how to deal with free convection. And as we have seen, the main driving parameter is the difference in temperature, delta T. So that's why we'll see that delta T will have the big effect on natural convection. Now, we'll not go through, if you want, the details of differential equations, but I just want you to know just the principles to understand how we define the parameters. So in fluids, you will learn how to write the continuity, momentum, and energy balance equations that are based on, for example, here, if you consider a steady 2D case of constant property conditions in which the body force acts in the negative x direction, we have that changes in density will affect the buoyancy force and density variations because only of temperature changes. That's why, okay, when you take fluids, you will see that the continuity equation in 2D can be written in the following form. While if you apply, if you want, like the Newton law for the fluid, okay, you have the following case. You have that, let's say, the acceleration of your fluid is related to forces acting on it. If we observe these terms, this is a force due to temperature difference. So this is the buoyancy force effect, okay? And this is what we call the viscous term, viscosity forces effect. So here we'll see that in natural convection, the dominant parameter is related to delta T, which is the temperature difference between the surface and the fluid, okay? And if we write the energy balance, for the energy balance for our fluid, we have, these are the convective terms, okay? And this is the conduction term. So you are already familiar a little bit with the energy balances, but within a solid. We have already considered energy balance within a solid. And in a solid, we have only transfer in the solid by conduction. While when you consider a fluid, in a fluid, you have both modes within the fluid, conduction and convection. So in steady state conditions, you can write the following form. What I care about mainly in these equations is to understand the importance of temperature difference in driving the flow in free convection, okay? Now, from this equation, we can determine also a new constant that is important for us, which is beta. What is beta? Beta is a fluid property known as the volumetric thermal expansion coefficient. It provides a measure of the amount by which the density changes in response to a change in temperature at constant pressure. So for ideal gases, we can write that beta is equal to 1 over temperature, okay? And this parameter will affect, if you want, the natural convection. That's why we are introducing it here. Now, if you have liquids and non-ideal gas, beta can be found from tables. Okay, so until now, we said that in convection, one of the most important parameter is the convective heat transfer coefficient H. And now the idea is how to evaluate H. And as we said, H is really complex. It's affected by the type of the moving fluid, the geometry of the surface, the roughness of the surface, etc. We already know from the introduction chapter in heat transfer that the convective heat transfer can be calculated as HA times delta T. So the convective coefficient H times the area times Ts minus T infinity. Okay, so the idea now is how to evaluate this H. So this chapter will be just, if you want, to help us into how to find H. To be able to understand how we should find H, we should first introduce a set of dimensionless parameters that will affect free convection, okay? So to compare the convective heat transfer efficiency between different geometries, it is better to use a dimensionless number for H. In fluids, you will see that dimensionless numbers are really important. For example, one of the main dimensionless numbers that we talk about is Reynolds number. Reynolds number, for example, has no unit, and it can help us to know the regime of the flow, if the flow is laminar or turbulent. So putting our characteristic variables in dimensionless form will help us into, if you want, coming up with general formulas that can be used in even if we vary values. Okay, so from here the importance of dimensionless numbers. And one of the dimensionless numbers that is very important in heat transfer, which is related to H, is called the Nusselt number. And the Nusselt number is by definition the ratio of conductive thermal resistance to convective thermal resistance. You know from chapters of conduction that the conduction resistance is L over K, while the convective resistance is 1 over H. So if you want, Nusselt will give you an idea about the ratio of conduction resistance to convective resistance to see what is the dominant resistance that we have. Okay, so if we divide conductive thermal resistance by convective thermal resistance, we get what we call the Nusselt number, where Kf is the fluid thermal conductivity and L is a characteristic distance. هلا we'll see the importance of this number when we in order to calculate H, because the idea is the following. We do experiments. Experiments will help us to determine Nusselt. And once we get Nusselt, how we can calculate H? We say that H is simply Nusselt number times K over L. Okay, so this is how we can use empirical relations, because empirical relations will give Nusselt. And once we have Nusselt, we calculate H. So this is the importance of dimensionless numbers, because they will give us general equations, general empirical relations that can be used to determine our convective coefficient. Now, what is the difference between local Nusselt number and average Nusselt number? If I go back with you to the previous example, you have a vertical plate and you have a natural convection and formation of a certain boundary layer over the plate, okay? If you calculate heat transfer at this level, it will be different than heat transfer here. Why? Because the thickness of the boundary layer is changing. So you don't have the same rate everywhere, okay? And because of this, H can be variable. So in case, or you have variation of heat flux, or you have variation of temperature conditions, okay? So whenever you have variation in parameters, this might lead to variation in H. And because you have H variable over your surface, then Nusselt also will be varying. So if you want to determine at a certain location, specific location, what is the convective coefficient H function of X, you need to define what we call local Nusselt number. So you need to define what is Nusselt number at any X. And then to calculate, for example, if I consider X this height, okay, Nusselt number will be H times X over K. And if I want to have the average Nusselt number, then I can define like an average coefficient H over the whole surface. And I define Nusselt average as H average times L over K. So if you want, once I have this function, I can deduce the expression of Nusselt average. And you will see that all of these will be provided to you. I will give you formulas for local Nusselt and for average Nusselt numbers. Now, what are the dimensionless parameters in a free convection? First, we can define what we call the Grashof number, okay? The Grashof number is related to buoyancy effects and temperature difference between the surface and the outer environment. So the thermal expansion coefficient beta is a measure of the amount by which the density changes in response to a change in temperature. So as we said, we have to create these buoyancy effects, we need a relation between density difference and temperature difference. And this is, you can get this from beta. This is the thermal expansion coefficient, beta. And we have seen that for an ideal gas, it can be calculated as 1 over the temperature. Okay, so this is a characteristic parameter that will relate the amount of density change relative to temperature change. Of course, higher the density change with temperature change, higher is buoyancy effects, and better is natural and free convection. Okay, so this is why the higher beta is, the better the free convection is. Okay, now we have that we can define a reference velocity for free convection given by the following formula. Okay, so you don't have to know how we get this. Okay, just you should know by that we can relate a characteristic velocity in natural convection to the temperature difference, delta T, to the thermal coefficient. So higher delta T, higher this velocity, so better is the free convection. Higher beta also, the better is, of course. Okay, so now we know that in fluids, we said that one very important number to characterize behavior of a fluid is Reynolds. And Reynolds is velocity times length over viscosity. Okay, so since we have the expression of velocity that is related to free convection, if we replace it here in this equation, we get an expression, okay, for a dimensionless number that is similar, if you want, to Reynolds in fluids, but we'll call it, okay, from here we'll call it Grashof. Grashof is this Reynolds number square. Okay, and the Grashof, if you want, is like Reynolds in forced convection. If you have forced convection, you blow air over a surface, you use Reynolds number as characteristic parameter. While if you have the case of free convection or natural convection, you use Grashof number. And as you can see, Grashof is depending on the gravitational value G, the thermal expansion coefficient beta, the value of delta T, the characteristic length. For example, for a vertical wall, the characteristic length is the height, for example. Okay, over the kinematic viscosity square. So this is the Grashof. You don't have to memorize these expressions. I will give them to you. You just have to understand that the purpose of our study is to get H. Okay, and to get H, we need to relate Nusselt number to parameters like delta T, beta, etc. Okay, to be able to, at the end, come up with empirical relations that will allow us to calculate H. This is the final purpose, and in the coming slides, you'll understand better what do we mean by this. Okay, now, as we said, Grashof is very important, but also the properties of the fluids, okay, will affect the behavior of the fluid. That's why we define, like, if you want, a dimensionless number combining the Grashof number, which is related to buoyancy effect, and the Prandtl number, which is related to properties of the fluid. And the Prandtl number, by definition, is the ratio of momentum diffusivity, mu, over thermal diffusivity, alpha. We have that the momentum diffusivity is dynamic viscosity over rho, while the thermal diffusivity, alpha, that you know from previous chapter, is K over rho Cp. Okay, so Prandtl number, if you want, represents the ratio between momentum to thermal diffusivities, and it will characterize the fluid behavior. Okay, that's why we say that when we combine Grashof dimensionless number and Prandtl number, we get a dimensionless number that is very important, okay, and that will B's that will replace Reynolds number in case of forced convection. So you should keep in mind, forced convection, I calculate Reynolds number to know what empirical relation to select, to know if it's laminar or turbulent. While in free convection, the empirical relations will be divided according to Rayleigh number. Okay? And typical correlations of Nusselt number in free convection are of the following form. And for example, I tell you, if you have Rayleigh between A and B, use C equal to 10, for example. If you have Rayleigh equal to, if Rayleigh is varying from B to C, okay, use another value for the constant C and M. So the values of C and M will vary depending on the Rayleigh value. So what you should do is the following. You have a problem in which you have free convection. You calculate Rayleigh. You obtain a number. Now you go to your relations. You see this number is in which range. Depending on the